The rigid bedrock of modern computing relies on classical Boolean logic. It is a system built entirely on absolute truth. In classical logic, variables are sharply defined and discrete. Every proposition must evaluate to one of two integer values, 0 for false or 1 for true. This binary framework is highly effective for calculating what mathematicians call stochastic uncertainty. Stochastic methods evaluate the chance that a precisely defined event will occur. For example, if a weapon fires, a stochastic calculation might determine the probability of hitting a specific coordinate on a target is 0.8 or 80%. The system breaks down entirely when the target itself is not a precise coordinate but a subjective concept. Probability calculus calculates the chance of an event, but it cannot process the vagueness of language. You cannot program a machine using standard probability to understand concepts that are inherently undefined. This introduces a distinct mathematical problem known as lexical uncertainty. This is the imprecision built into the words humans use to evaluate concepts and draw conclusions. Consider a corporate projection stating, "We will probably have a successful financial year." The event itself is not clearly defined. Successful is a subjective, lexically uncertain category. In 1965, mathematician Lotfi-Zadeh published a formal system designed specifically to solve this lexical problem, introducing the new concept of fuzzy sets. This text explicitly defines fuzzy logic. It is a many-valued logic system that expands knowledge representation beyond crisp binary membership. Instead of restricting variables to 0 or 1, truth values in a fuzzy system can exist as any real number in the continuous interval between 0 and 1. The name itself is often misunderstood. Fuzzy logic is not an imprecise methodology. It is a rigorous mathematical extension designed specifically to compute partial truths. This chart shows how a classical, crisp set attempts to categorize the concept of tall men. The system establishes a strict vertical threshold at exactly 170 centimeters. The logical failure here is immediate. A man who measures exactly 170 centimeters returns a value of 1. But a man who measures 169.9 centimeters maps to a 0. The system evaluates him as completely not tall. The fuzzy approach eliminates this strict hard line, replacing the vertical cliff with a continuous mathematical curve. Re-evaluating the height data along this new slope yields a much different result. A man measuring 181 centimeters now maps to a real number value of 0.86. That 0.86 is his grade of membership. He does not perfectly belong to the category, but he partially belongs to the set of tall men. Zadeh's framework is often compared to evaluating a half-eaten apple. A fuzzy set allows the object to transition smoothly from apple to not apple. The physical object holds a partial membership in both sets simultaneously, each to a specific degree. Discarding binary thresholds in favor of continuous slopes allows logical systems to accurately reflect physical reality rather than forcing data into artificial constraints. To make vagueness computable, it must be completely characterized by a strict mathematical formula. This equation represents a fuzzy set. This diagram illustrates the membership function. It maps domain elements to their exact degrees of belonging. Within this geometry, the support represents all elements with a membership grade greater than 0. The core is the subset possessing an absolute membership grade of 1. If a given subset possesses at least one element in its core, it achieves the mathematical status of a normal fuzzy set. By isolating vague adjectives into defined geometric regions, cores, supports, and boundaries, engineers successfully mathematologize human subjectivity. This chart maps multiple membership functions across a single universe to create a fuzzy partition. At crossover points, a single age, like 30, simultaneously triggers fractional membership values in adjacent sets, belonging partially to young and middle-aged. To process these overlapping values, classical set theory operations are adapted for fractional numbers. In a union operation, the logical OR, the system identifies and extracts the maximum membership value between the overlapping sets. For an intersection operation, the logical AND, the system isolates the minimum membership value between those sets. And for the complement operation, the logical NOT, the system subtracts the membership value from 1. While the linguistic inputs are vague by design, The internal logic operations are executed via strict, deterministic min-max algebra. In physical applications, fuzzy logic is typically deployed when a mathematical model of a mechanical process is simply too complex to encode using traditional methods. The pipeline that makes this control possible is the fuzzy inference system. In Step 1, the fuzzifier, precise sensor data, like an exact room temperature, enters the system and is mathematically mapped to a fractional truth value on our membership curves. Next, the inference engine evaluates those truth values against pre-programmed rules. This architecture allows engineers to program industrial machines using the natural semantic knowledge of an expert, rather than thousands of lines of brittle Boolean thresholds. There is one final required step. The physical hardware requires an exact command to operate, so the aggregated fuzzy rules must pass through the defuzzifier. The defuzzifier calculates the center of gravity of the combined fuzzy outputs, returning a single, distinct integer to the machine. This continuous logic creates immense efficiency. One single fuzzy rule can replace dozens of conventional crisp rules. Classical computing uses statistics to predict the probability of a precise event. Fuzzy logic abandons chance entirely. It provides a formal system to compute the degree of truth for an imprecise event. By utilizing this framework, engineers proved that human subjectivity is not a flaw in reasoning. It is a highly evolved, continuous computational heuristic that machines can reliably replicate.